right, you guys, we're going to go through section 5.6 notes here, and this is on compound interest. So application problems, right? These are like real world examples, right? When are we ever going to need this, Mr. Rodriguez? Well, here you go. This is when you're going to need it. So these are examples in the real world where we see exponential growth and we see exponential equations and log equations to solve. So any of you interested in going into finance in your future, or investment banking and stuff like that, you will definitely see these exponential equations. So just a quick little example to get us started. Suppose you want to increase 100 by 15%. Well, you take 100 plus 100 times the 15%, and you get 100 times 1 plus 0.15, and you get 100 times 1.15, right? And so let's see if that's the same, right? So you just, when you work this out, right? If you, whoops, my pen is not on, hold on. When you work this out, you just get $115, right? If you had $100. So an amount of $100 is increased by 15%. So that gives you that $115, right? Then the new amount is increased by 15%. Okay, so if I have $115 and then I increase that by another 15%, that's like multiplying by 1.15. Okay, and you guys are gonna, let me grab my calculator. And so I get 132.25. Right, so that's what I get when I do the 115 times another 15%, and et cetera, et cetera. Is this the same as an overall increase of 30%? So let's see what that would mean. If I had an overall increase of 30%, well, that would be the original $100 plus 100 times a 30% increase, right? Which ends up just giving us $130, right, when you multiply this out. And so which one is bigger, right? Obviously this one. So this is what we call compound interest versus just a one-time interest of 30%. So if you take 15% and then later you take 15% of that same amount, of that new amount, of the new amount, and then take another 15% of the amount, that interest is compounded. So compound interest is definitely more. And it's because of this exponential growth. And so there's formulas for compound interest. This is interest that's compounded annually. We have one formula, but you can also compound that interest at different times. So this is compounded once a year. It's an annual interest rate, compounded annually. And this is our formula. Okay, so what do all these variables mean? A is the amount in your account after, right? Amount after T years. P is the principal balance. Principal just means the starting or original balance of what you put into the account. 1 plus R, R is your interest rate. And what you want to do with that interest rate is you always want to rewrite it as a decimal. So if it's 5%, you would rewrite it as 0.05, right? 20%, you would rewrite it as 0.2, okay? So rewrite that interest rate as a decimal, and T is just time in years. This is an annual interest rate that we're talking about, okay? So example 1B, suppose you place $1,000 in a certificate of deposit, or called a CD, at an interest rate of 10%. So we've got some variables here. $1,000, that's going to be our principal, so that's going to be P. We've got 10%, so that's going to be our rate, and again, we're going to change it to a decimal, so 0.10. How much will be in the account at the end of 3 years? So that's our time. And so I'm just going to use my formula, and this is just going to be a plug and chug, right? So I placed $1,000, that's my principal. 1 plus 0.10. Time is 3 years. Oh, so I'm trying to do, hold on a sec. I'm trying to pull up my calculator. Haha. so that I can kind of look at it both at the same time. That's so much better. Okay, so just type that in your calculator. You get 1,331 as my amount afterward. After 3 years, okay? And again, that's a compounded annually interest rate. So some of these problems are very straightforward. You just have to know what all the variables represent. You just plug it in and work through it. Example 2, we're going to maybe have to work backwards here. So suppose that $2,000 is invested, so that's still our P for principal, at a 7.5% interest rate. That's 7.5, but we change it to a decimal, so 0.075 is going to be our R. Interest compounded annually. So again, this is our annual interest rate formula. How many years will it take for the money to double? So for that to double, that means we want my amount at the end to now be $4,000. So I just use my formula. So 4,000 is the amount I want it to be. 2,000 is what I started with. That rate was 0.075, and I'm trying to solve for t. Okay, so this is now an exponential. So we know our ways to solve exponentials would be to use a log, right? And so what I'm going to first do is simplify this a little bit, divide by that 2,000. So I'm going to have 2 equals 1 point, I can add those together, right? 1.075 to the t. So now I would just use a log, right? I would rewrite this exponential equation in order to get your variable out of the exponent. You're going to switch from exponential form to log form. So I'm going to rewrite this as a log. So this is now going to become log base 1.075 of 2. That's going to equal t. I'm just switching forms. And so now I would type that in my calculator. So log base, right? We talked about this in the calculator, so I have to go to math. Log base. My base is 1.075, and my argument is 2, and there is my time. Okay, now we want to know how many years will it take. So 9 years is not enough, and it's asking for actual years, so I would round this up to 10 years. It didn't say what to round to. You could leave it 9.58 years, 9.6 years. If it's looking for a whole number, though, I would go ahead and put it at 10 years. All right, so that's compounded interest annually. That formula I have seen on the SAT. Some of you in SAT prep with me have seen that formula on a couple SAT prep problems, problem-solving types. So they do expect you to know sort of that basic format of a compounded interest. Now, what if we're not compounding it annually, but we're compounding it at different points throughout the year? Well, you're going to make more money, right, if it compounds every month instead of once a year, or if that interest compounds every day, right, or something like that. So there is a change to this formula if we're looking at interest compounded at n times per year. Okay, so we still have that annual rate R, we still have principal P, but now it's being compounded n times a year. So what's going to happen with our formula is going to change a little bit, and what's going to happen is you're going to have to take R divided by n here, and then up here it's going to be n times T. Okay, so there's a little bit of difference in there. Again, this is n times a year. So for example, if it said like, let's look at this next example, right? If it's compounded once a year, n is just 1, and that brings us back to the original formula, right? If I just have n of 1, well, what does that look like? That's just 1 plus r to the t. That's my annual interest rate, right? So my annual compounded interest. So that one is still the same formula. But if I do it quarterly, what does quarterly mean? Quarterly means quarters 4. There's 4 quarters in a dollar. Quarter is 4. So that means n equals 4. Some other common ones that you'll see, monthly. Well, how many months are in a year? N would be 12. Quarterly we just talked about. N was 4. Weekly, N would be 52. There's 52 weeks in a year. Daily, N would be 365. You can just leave it 365. Okay, so there's different, how many, you just divide the year into that many number of segments, and that would be your N. Okay, so compounded quarterly means 4 times a year it's going to be compounded. So our N is going to equal 4. $1,000. Oh, we're going to go ahead and solve this one. Sorry. $1,000. 10% is our interest rate. And at the end of 1 year, they want it. All right, so this would just be 1,000 times 10. This is, right, you guys could kind of do this one in your head. 1,000 times 0.10 is just, or 1.110, right? $1,100. At annual interest rate, compounded once a year. What about compounded quarterly, though? So we take that same principle, the same rate, but now we have to divide it by 4, and then up here in the exponent, we have to do 4 times 1, N times T. Okay, so when I work this out now, again, where's my calculator? This is where so I've got 1.114. I'm going to raise that to the 4th power and then multiply it times 1,000. All right, so I ended up getting $1,103.81. Okay, so not much of a difference, right? $3 difference for compounding quarterly, but if you had a larger principal in there, right, and if you did this over 20 years, right, you would definitely see a difference when it's compounded more frequently. Okay, so that's the compounded N different times in a year. Moving on, there's one more compounded interest formula. So what if we go more and more frequently here? So we talked about, right, here is our formula. This is just that, like, the basic part of inside the parentheses without the principal involved, right? What happens if we just do it annually, right? N is 1, 1, 1, so we just get this answer of 2. When we do it semi-annually, that's an N of 2. We end up getting 2.25. If we do it quarterly, 4 times a year, we get 2.44. So you see how much this is increasing, right? And so we are getting a better rate of return. When it's monthly, N is 12, we get to 2.61. Daily, we can even go better. What about hourly? What if it compounded every hour? Okay, that number is getting bigger. What if it was every minute? Okay, and then what if it was every second, right? Okay, so what I want you to notice is look at these numbers over here on the right. Okay, they're getting closer and closer, and these ones are getting really kind of to be pretty much the same number here. What actually happens is this number, maybe you recognize it, this number is E. All right, it's the base of our natural log. That's E right there, right? That's what these numbers come to. So that's really where E comes from. It's kind of cool. It's like the derivation of where E is. And if you kept compounding it even more and more, like milliseconds and semiseconds, and I don't even know the words for those, right? Until you're literally compounding continuously. Like you are at a continuous compounding, then that base becomes E. Okay, and we have a little variation on our formula. And so what do I mean by that? It means that our formula changes to A is still there, P is still there, but now this base that's on the inside, so instead of before being that 1 plus your rate over N, right, that whole parenthesis part has now turned into E. Okay, it's still raised to the R times T, the rate times time. Okay, that's still up there. But the E is now your base, okay? So this is our new formula. And this formula is what you're going to use anytime it says compounded continuously. So those two words together are what you want to look for. So if you see compounded continuously, you must use this formula. It's A equals P times E to the RT. I call it the PERT formula. You guys ever heard of a shampoo? It's called PERT Plus. It's like this awful green shampoo. It came out in like 1985. Yes, I'm that old or something. And it was this green shampoo, and it was like the first 2-in-1 shampoo and conditioner in one. It was like a big deal back then. Believe me, you guys, this has not always been a thing, okay? So it was like the first deal of shampoo and conditioner together, right? It was called PERT Plus. It was awful. And it didn't smell that good either. It was fine, but it was like a big deal. PERT Plus, there are all these commercials, people with PERT. I don't know if it's still out there. I should go look at the store and see if they still sell PERT Plus. But I always think of PERT Plus when I think of the PERT formula for compounded interest, because it's P times E to the RT, right? That's our formula. So it kind of says PERT in here. So if that helps you remember it, just think shampoo and conditioner all in one. All right, example 5. So let's work through a problem here. Again, if you see those words compounding continuously, you automatically write down the formula P E to the RT. Principal was 1,600. E is just E. 5% is my rate, so I rewrite it as 0.05. It wants to know when will the balance reach 2,400. So I don't know T, but I know that A is 2,400. All right, so again, we've got an exponential here, and our exponentials, we always solve using a log. So I'm going to go ahead and divide by 1,600 first. Remember, in order to rewrite this as a log, you have to isolate that exponential first, right? So I isolate the e to the 0.05t. So that's isolated first. Now I can rewrite this as a log. So this is natural log of 1.5 equals 0.05t. Divide by 0.05. And there's when I need my calculator. Natural log of 1.5, whoops, divided by 0.05. So 8.1. Does it give me, yeah. Oh, how do I get rid of you now? Go away, calculator, I don't want you anymore. There it goes. Okay. It didn't tell us what to round to, so we'll just leave it, sure, 8.109. Again, if it doesn't tell you what to round, I think on your tests, I do tell you what to round to. Okay, so I'll be pretty specific on those. All right, so let's do a couple more examples with this compounded continuously. We'll do 2 more examples. A principal of $100 is deposited in account number 1. So we have an account number 1, $100, 6%, compounded continuously. All right, so let's set up account number 1. $100 compounded continuously means we're using PERT. So E to the RT. Okay, there's my equation for account 1. I don't know what time is yet. We have another account here. I'll highlight it in different color. Also $100. Account number 2, also 6%, but this one is compounded only once a year. So for account number 2, I'm going to need to use annual interest rate, right? So that was this one. A equals P, 1 plus R to the T. Equals P, 1 plus R to the T. Okay, so notice we had a compounded, right? This is compounded continuously. This was annual. So different formulas for each of those. Use a graphing calculator to determine how long it will take until the amount in account 1 exceeds the amount in account 2 by at least $10. So basically what it's asking us to do is graph these. That's why it's saying using a graphing calculator. So I'm going to graph these two, and I'm going to see when account number 1 is bigger than account number 2 by at least $10. Now we know compounded continuously is going to surpass compounded annually, right? It's compounded more frequently, it's going to be higher. But we want to know when it's going to exceed it by at least $10. So here's my calculator again. So I'm going to go to y equals, and I'm going to graph both of these. So the first one is 100 e to the 0.06 t is just x, right? That's my variable. Equation number 2 is 100 parentheses 1 plus 0.06, close my parentheses, raise it to the x power. Okay, so I'm just typing both of those into my y equals. And now I'm going to go ahead and graph them. There they are. I'm going to have to zoom out here. The nice thing about using this this graphing calculator, here I want to give it a little bit more space so you guys can kind of see it. On the calculator, it's kind of cool because you can kind of zoom in and zoom out just by touching your screen. When you're doing it on your actual calculator, you're going to have to just play with that window a lot, right? Zoom in, zoom out, go to window, adjust it. So I definitely noticed that at the beginning they're kind of similar, but that green one is starting to surpass the red one. And we want it to surpass it at 10 or more, right? At least 10. So the best way to do this is actually going to look at the table and start to compare. So I'm going to go to table here. There we go. And I want to compare these two to see when that difference, right? I want that difference between the two to be 10, at least $10. 245, 239, nope. 261, 254. We're getting there. Close. That's 285 to 294. All right, so here it is, I think. 302.5 to 312.6. So that's more than $10. So that would be our solution. Oops. I don't know where that went. That's weird. So it looked like I was there. It was. So what year is that? That's year 19. Okay. So I think we're going to say year, I don't know why it disappears like that. That's weird. What if I brought it over here? Okay, it was weird. So it looks like year 19. What we noticed is that account number 1 was, what did I say, 312 point something, and account number 2 was like 302. It was a little less, right? Was that exactly it? Let's see. Oh, I don't know what's happening there. Yeah, 312.678, and then 302.56. Okay? So you guys see that comparison there. Okay. So it looks like our answer is year 19. So it'll take 19 years for it to surpass it. And again, just using the table function in your calculator is what's going to help there. All right, last example. Compute the doubling time. All right, so this idea of doubling time. What is doubling time? Doubling time is just the time it takes to double an amount, right? When a sum is invested at an interest rate of 4% per annum, compounded continuously. Again, as soon as I see that, I write down PERT. I know 4%, so that's really the only thing I know so far. So I need a little bit more information here. Well, it's asking about doubling time. It wants the time it takes to double. So I'm looking for time. That's going to be what I'm looking for. The principal I'm not sure of, but the A here is going to have to be double the original, right? So double, if my original is P, double the original would be 2 times P, right? So that's what I'm looking at. And now what I can do is divide by P, boom, boom, and now I have an equation I can solve. All right, so those p's are gone, and it's just 2 equals e to the 0.04t. Rewrite this as natural log, divide, calculator. Oops. Hold on. Oh my gosh. I don't know how to get out of this. There we go. I don't know why it's so small. Do you guys see this weird? It's so weird. I don't know why. Okay, sorry about that. Calculator issues. All right, so natural log of 2 divided by 0.04. 17.3 something, something, something. There we go. All right, get out of here, calculator. You're weird. All right, 17.3 years. Boop, 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 boop. That's it, okay? So that would be our doubling time. This concept of doubling time, we're talking about this in our notes tomorrow too, our next class, about like half-life and doubling time. It's gonna be a very similar sort of technique here that we just saw on that problem. All right, so good luck. You've got a homework assignment tonight in your practice packet, so work on that, and I will see you